Yes, sir. And the YouTube viewers are waiting, sir. Shall we start, sir? Now?
Yeah, I think we should start because this one, out of 100, only 43 are in. Let them join.
Yeah, yes, sir. Sir, Principal, sir, shall we start, sir, now? Principal. Sir, Principal, sir, shall we start, sir? Sir, you are on mute, sir.
Shall we start, madam?
I will start, sir, because YouTube viewers are waiting.
I like to start.
Okay, sir.
Good morning, sir.
Good morning,
sir.
Dinesh.
Thank you, sir.
Good morning, sir.
Good morning.
Morning.
So, good morning, one and all joining in this online webinar conducted by Civil Engineering Department of our institution. The management, HODs, faculty members, and students, I wholeheartedly welcome distinguished resource persons, Professor CVR Murthy sir, Dr. Rupen Goswami, and Dr. KP Jaya madam, and Dr. STG and Dr. SR Satish Kumar for accepting our invitation to conduct this webinar in the topic Indian Seismic Codes conducted by Civil Engineering Department of our institution. I wholeheartedly thank and welcome distinguished resource persons on behalf of our beloved chairman, sir, members of the management, and all of us. And I also welcome all the allied participants who are joining in this webinar by registering themselves during this lockdown period. So I would like to thank all of you for your interest to attend this webinar. So my dear participants, definitely it will be very useful for your career. And I would like to thank the HOD Civil Engineering and also faculty members of Civil Engineering Department for organizing this 5 days webinar on Indian seismic codes. So on behalf of all of us, I would like to thank once again all the allied participants who are joining in this webinar. So my dear participants, during lockdown period, this is really an unexpected one. We never ever expected this kind of situation in our lifetime. So to make use of this period, all the institutions are conducting webinar in the latest topics by the renowned resource persons like our distinguished resource person who are going to address you for these 5 days. So to make use of this opportunity, so please interact with the resource person at the end of each webinar, and you will have to make use of this for your benefit. So to introduce our institution to all the participants, I would like to share a few slides. Our institution, RMK Engineering College, is established in the year 1995 and at Kavaripete, Komudipundi Taluk, at a distance of 30 kilometers from Chennai. The college is managed by Lakshmi Kantamal Educational Trust, and our institution is at the forefront of engineering education consistently for the last 25 years. One among the top 10 engineering colleges, and in 2019, 18.6 graduates, and overall result in 2019 is 93.82. So from its inception, our students have bagged 955 university ranks, including 23 gold medals. And we have signed 24 MOUs with foreign institutions and industries to enrich the knowledge of our students and faculty members. With respect to placement opportunity provided to our students by our institution, there are 200 plus regular recruiters every year, and we have been maintaining consistently above 85% of annual placement conversion to provide the complete education during the long day one campus placement 2020 in the Cognizant 299 offers and TCS 191, Wipro 168 and Infosys 158. Totally 816 offers have been issued to our students. And our management team led by our founder chairman, visionary R.S. Muniratnam, a dynamic personality, a great visionary and philanthropist. At present, he is holding a post of president of Consortium of Self-Financing Professional Arts and Science Colleges in Tamil Nadu and chief patron of All India Federation of Self-Financing in Technical Institutions across the country. He is also honorary advisor for Youth and Sports Development Departments, Government of Tamil Nadu. He has received Vidya Ratna Award recently. And our management team consisting of our chairperson, Madam, Director sir, Vice Chairperson madam, Vice Chairman sir, Trustee, and the Secretary. And our institution started in 1995. So this is 25th year, 25 years of excellence in technical education, approved by AICTE and affiliated to Anna University. All the UG programs are accredited by NBA. We have 7 UG branches and 3 PG courses. All the UG branches are accredited, and our institution is accredited by NAC with A+ grade and accredited by TCS with B grade, and we have been maintaining 1:15 faculty ratio. And there are 7 departments recognized by Anna University as research center to pursue PhD. So around 60 faculty members are recognized supervisor in the Anna University to guide the PhD scholars. And with respect to the achievements and recognitions of our institutions, I would like to share the very important recognitions. In the year 2008, we have received the best overall performance from ISTE New Delhi. And in NIRF India rankings 2019, our institution is shortlisted in the 157th position out of 200 institutions across the country by MHRD Government of India. With respect to cleanliness and greenery maintenance inside the campus and hygiene maintenance inside the campus, so we have achieved 6th position in the Swachhta ranking across the country. So in the AICTE CAI survey of best industry linked institute, starting from 2015 for electronics and 18 CSE and IT, and 2019 mechanical and allied engineering branches have got this AICTE CAI award. So from the inception, there are 96.11 graduates. A total of 14,554 students received their degree within the stipulated period of time, 4 years. And we have to have industry connect. We have established 14 Center of Excellence laboratories in collaboration with the various top MNCs. Our institution is accredited by NAC with A+ grade, and NAC has approved our institution to mentor 10 institutions. So we have received a Best Institutional Food Safety Award by Government of Tamil Nadu. We have also organized a TEDx during last year. And with respect to the Smart India Hackathon conducted by MHRD Government of India, our students are participating every year. And in 2018, 2 teams won first prize in software. And in 2019, totally 3 teams, including 1 team in hardware edition, and 2 teams got first prize in software edition. And in 2018, institution is identified as nodal center to conduct the Smart India Hackathon out of 28 nodal centers identified by MHRD across the country. Our Honorable Minister, Honorable Sri Hardeep Singh Puri, Minister of State for Housing and Urban Affairs, have felicitated during the valedictory function. And our students have also received AICTE Chhatra Vishwakarma Award. And to inculcate entrepreneurship among all the students, we have MSME Incubator, ECEL approved by EDI. And also to help the nearby villages, our institution adopted 5 villages in and around our institution under Unnat Bharat Abhiyan 2.0 scheme, MHRD. And our institution is ranked 4-star rating by MHRD's Institution Innovation Cell, IIC. With respect to top magazine rankings, DataQuest in the 2020 recent survey across South India, so our institution rank is 10th rank. And in the private engineering institutions across the country, 13th rank, and including government and private, out of top 100 institutions by DataQuest, position is 22nd position. Similarly, we consider 26th rank, and by India Today, 30th rank, and 92nd rank by Outlook. And regarding the COE laboratories established in our institution, there are 15 COE laboratories in connection with, in collaboration with industries like Cognizant, TCS, Virtusa, Salesforce, Hitachi, Wipro, and KPIT Technologies. Mitsubishi has also sponsored hardware and software for this factory automation lab. And with respect to civil engineering department, in collaboration with L&T Constructions, we have concrete and formwork COE laboratory. And these are all the laboratory inaugural photographs along with the industry person and our distinguished chairman. And we have been conducting training activities for all of our students to provide 360-degree training with respect to enhance their logical ability, quantitative, personality development, technical skills, and also communication skills. Our students are getting placement in top core companies, including product companies. And this year for 2020 batch, till March 17th, our placement percentage is 88%. So with respect to other infrastructure facilities like library, health center, transport, sports, hostel facilities, and general amenities and computing facilities, so we are fulfilled with all the requirements and the expectations of all the stakeholders. Apart from all these activities, we have eCell, and with the help of this eCell, those students who are interested to become an entrepreneur, those who want to start their own company, we are encouraged themselves by conducting so many programs with the help of EDA and also MSME. Every year, 5 to 10% of students are becoming entrepreneurs. During their third year and final year itself, they have registered their startup through MSME startup. And the Center for Higher Education take care of all the students who are opted for higher studies, and 15 to 20% of students every year joined in reputed institutions, including IIT for higher education in India and abroad. Apart from these centers, we have Center for Foreign Languages, particularly Japanese language. Around 5% of students are getting involved in this Japanese language training program and getting opportunity to join in Japanese companies. And we have Center for IPR and Patents last year. So we have filed 17 patents in the past 2 years. Totally 27 patents have been filed by our faculty members and students, and out of which 4 faculty members patent application has been published and yet to get the grant of approval from Patent Office. And we have Center for Online Learning for faculty development. We have a library with a very good number of books and journals. We have subscribed for all the e-journals. And with respect to sports facilities, hostel facilities, and general amenities, we have effluent treatment plant and also RO plant to provide purified water for our students. And we have bank, ATM, and postbox facility inside the campus. And to provide uninterruptible power supply, so power generator with full capacity, 1105 kVA genset is available in the campus. So these are all the facilities, and we are also encouraging our students to participate in state level, national level, and international level competitions, and they are bringing a lot of laurels to our institution. Similarly, our faculty members are also motivated to attend various programs and also publish their papers and submit their proposals. So thanks for joining in this webinar. Once again, I would like to convey our sincere thanks to our resource persons who have accepted our invitation to conduct all the participants of this 5 days webinar conducted by Civil Engineering Department. We have a very strong alumni association. Recently, last year, our chairman started USA Alumni Chapter and conducted at 5 places around 500 alumni of our institution attended this meeting conducted at San Francisco, Los Angeles, Atlanta, and Washington, and New York with their family members. And we have also inaugurated USA Alumni Chapter during this visit. So other institutions from our management, RMD Engineering College, RMK College of Engineering and Technology, one Polytechnic, Durga Devi Polytechnic, and there are 4 schools. 3 schools are situated in and around Kavaripettai, and 1 school at Thiruvarkadu, Chennai. Thank you for the patient listening. And once again, I thank the resource person and Department of Civil Engineering for organizing such a great event with more number of participants across the country. Thank you. Thank you for the given opportunity. Now I request Civil Engineering Department HOD Dr. Binu Sukumar to proceed with the webinar.
So, good morning, all of you present here. So, I got my net disconnected. Sorry for the delay. So, good morning, all the participants and eminent speakers. I'll just share my presentation. I'll give a brief introduction about the department various activities. So good morning once again, all the participants and eminent speakers of the 5-day webinar on Indian Seismic Code IS1893 and IS13920. So I'll brief various achievements and accolades won by the students of Department of Civil Engineering. So department has started in the year 2006 and 10 batches have successfully completed with a 91.3% of graduates passed out with 80 university ranks and 3 gold medals. And Mr. Satish Kumar and Loganayagi and Lakshmanan brought laurels to the department. And we were fortunate to have eminent speakers visited our department to enlighten our students. Padma Bhushan, Dr. A. Ramakrishna, former Deputy Managing Director, L&D Construction, and prayers for the departed soul. And Dr. A. R. Shantakumar, former Dean and Chairman at Anna University. And this is a team of the expert distinguished speakers of the webinar arranged for 5 days. Dr. C. Vyamurthy, KP Jaya ma'am, Rekukant sir, Satish Kumar sir, and Dr. Ruben Goswami. Except Ruben Goswami, all others have already visited our campus and enlighten our students during various occasions. Am I audible, sir?
Yes, you are audible.
Yes. And many of the senior professors from IIT Madras have visited our campus and during various occasions, various programs organized by the Department of Civil Engineering and enlightened our students. And the professors from IIT Madras, IIT Delhi, IIT Bombay, NIT Trichy, NIT Calicut, and scientists from IGCAR Kalpakkam and scientists from SERC. And they have shared their experience during various occasions of programs organized by the Department of Civil Engineering. And we had Dr. V.K. Reina, renowned consultant and some industrial experts from L&D Constructions, professors from Anna University, and BIM experts and structural consultants. So during various occasions, they gave guest lectures for our students. And we were fortunate to have such eminent people visited our department and shared their experience with our students. And a few of the awards and achievements for the students. During 2014, we have received Construction Industry Awards for the Excellence in Civil Engineering Education and Best Student Project Award, and 2 teams from the Department of Civil Engineering won second prize in concrete canoe competition held at IIT Madras in association with Indian Concrete Institute. And in ICI Ultratech Award in 2 consecutive years, 2015 and 2016, for Outstanding Student Chapter of Tamil Nadu, and Best Engineering College Award for during 2017 by Institution of Engineers India. And students are also bringing laurels to the department, a few of the awards and accolades. Mr. Saran Kumar won Best Student Researcher Award by Institution of Engineers India, and also Mr. Lakshmanan won Best Student Academic Award. Saran also won the prize of Best Student Award for the year 2018 from IST. And during 2019, Mr. Sambashiva Rao received Research Innovation Award, and Ms. Jayanti received Best Student Award from IST. And some student, Ms. Preeta, won first prize in the paper presentation competition. And Mr. Madan Kumar received Shimoga Open Second International Karate Championship. And our alumni are placed in very good reputed positions. Some of the distinguished alumni, Zarina Basha, she's a technical officer in IGCAR Kalpakkam. Now, currently she is pursuing MS in structural engineering at the University of Calgary. And Sashank, he is a 2014 batch, and he is a project engineer at Mass Building and Bridges, Boston, after completing his MS program there. And the 2014 batch, Mr. Lokeshwaran, is the 2018 cadre IPS officer. And Mr. Kannan, he's a successful entrepreneur. He was receiving Distinguished Alumni Award from our chairman, sir. And Mr. Ivaraj, 2014 batch, he's at the verge of completion of his PhD program with NIT Madras under the guidance of Dr. Manu Sundaram, sir. And he was receiving Young Researcher Award. And students are actively participating in various industrial visits, in-plant training. And our one batch of our students participated in the Smart India Hackathon 2019 grand finale held at IIT Mumbai. And we have an institution innovation council very active, and students were explaining their project demonstration. And we have, in association with L&D Construction, we have a Center of Excellence in Concrete and Formwork, and 3 batches have completed their training there, and they have been recruited by L&D Construction. And our students are employed in various core MNC companies and software companies. L&T, Perry, BlueScope, Shapoorji Pallonji, BRG, BGR Energy System, KEC International, URC Constructions, Zamim Steel, Technip, Saipam India Limited, Mastro Steel, and other software companies also. They are been selected. And present final year 2 students won 5 offers, Ms. Lavanya and Gunashilan, 4 software companies and 1 core company. And many other students are also got many offers. 2 students 4 offers, and another 3-4 students got 3 offers each. So placement is very good in our department, in line with the institution. And many of our students are successful after completing their UG program. They have gone for higher studies in abroad, top level universities, and they are working in top level MNCs there. A few of the alumni have been listed here. And successful entrepreneurs, many of our students have taken up startup programs, and Mr. Vikas of 2012 and Kannan, they are very successful in their projects. And some of the few alumni, they are very successful, Sanjay Raj, Sai Krishna, and Mr. Abhilash. And department is very keen on research and development activities. And we have 45 lakhs of funded projects already available, and few other projects are in the pipeline. And 2 patents have been filed, and few other patents that we have applied and to get filed. And why Department of Civil Engineering, RMK Engineering College is preferred, and mainly because of the proven academic records and very good interaction with the industry collaboration. And we have a collaboration with L&D Construction for the Center of Excellence. And we are providing internship in IITs and top companies. We have structured training program and qualified and experienced faculty member, the ratio 1:15. And we have a very good clean and green campus. And we are encouraging the students for online certification courses. And the college is well connected through transport, and the institution is accredited with NAC A+. And we have the department is accredited with the NBA. And there are so many other reasons for choosing Department of Civil Engineering at RMK Engineering College. So I'm just I've given a brief intro about the department activities. So thank you for the patient listening. And now I'll just give a brief introduction about Professor C.V.R. Murthy. Does not need any introduction, but still I will give some important points about Sir. And he's a professor of civil engineering at IIT Madras. He took his BTech in civil engineering and MTech in structural engineering from IIT Madras, and PhD in earthquake engineering from California Institute of Technology, USA. Started his career at IIT Delhi during 1992. From 93 to 2010, nearly 17 years he has been serving IIT Kanpur, and joined IIT Madras during 2010, and currently he is working at IIT Madras. So Professor Murthy's primary research interests are studying seismic nonlinear behavior of steel and RC buildings and bridges, developing displacement-based design of structures, and preparing seismic design codes. And he has supervised many PhD and master's theses. He has been a member of earthquake reconnaissance team, which conducted extensive post-earthquake surveys, and some of them were part of Earthquake Engineering Research Institute, USA. He has been associated with major revision of Indian Seismic Code as member of Bureau of Indian Standards and Indian Road Congress. He has received ICI Best Construction Technique Paper Award. He was editor-in-chief of World Housing Encyclopedia, Earthquake Engineering Research Institute, USA, and principal author for National Disaster Management Policy and Guidelines by NDMA Government of India. And he was an honorary advisor, Earthquake Mitigation, Government of National Capital Territory of Delhi. And he is the member of Tamil Nadu State Disaster Management Authority, Government of Tamil Nadu. And he's a fellow member of Indian National Academy Engineering and a fellow of Institution of Engineers. And he's a life member of Indian Society of Earthquake Technology, Indian Rod Congress, Indian Concrete Institute, Institute for Steel Development and Growth, and life member of Indian Society of Advanced Material and Processing Engineering. He's a life member of Indian Archaeological Society as well. He has more than 100 publications with more than 1,000 citations with Index 14. We are indeed fortunate to have such an eminent person here to give an overview of Indian seismic codes. And welcome you, sir. And now you can please start your session. And once again, I welcome all the eminent speakers who has come here for the inaugural function, and subsequently for from tomorrow onwards, we'll be going to hear from all the eminent speakers, and they were the architect of the framing of the revision of IS Seismic Code. And thank you so much for accepting our invitation to be here with us, sir. So please, you can start your session, sir.
Thank you, madam. I thank the principal, Professor Junaid, and Madam Binu Sukumar for inviting me to this webinar. Today, I will present to you an overview of the Indian seismic codes. This is an effort that we started in about 2016 to harmonize and bring to perspective all the Indian seismic codes and raise their bar from where they stood at that point of time. And so I'll tell you a roadmap that we have set for ourselves in what we are going to achieve in the next 5 to 10 years. So today I'll talk about the past standards, the present condition of the standards, and then what we are likely to see in time ahead. Before I move into talking about the standards, I'd like to clarify one main point, that is about earthquakes. Unlike all other loads, earthquake loading is not a force applied on the building, but it is actually a movement under the building. And so this is not usually taught in the undergraduate program. How do you analyze buildings when there's a dynamic movement under the building? When I say this as part of the mandatory curriculum, we don't have. Some colleges have it as part of the electives. So the catch was that we were taught fixed base structures, force applied on them, and now we have a ground moving problem. So Indian standards made it simpler for the designers by providing an equivalent force that would get generated or could get induced in the structure and then use that as a basis for the design of structures. So this one main difference we have to keep in mind, that the earthquake is applying a movement under the building and not a force on the building. Force is induced as a consequence of the presence of mass. So that is called the inertial force that is induced during earthquake shaking. Another important point about earthquakes is that earthquakes are cyclic loading on structures. Meaning, unlike in the case of wind, where there's a basic pressure and a small flutter on that, earthquake is actually complete reversal about a mean zero, where you will see negative and positive faces exchanging their positions. Also, under wind loading, the design philosophy is that the structure should not have any damage. This is because wind is a recurring phenomenon, and we do not want to see that damage is accrued on a regular basis on structures. However, the extreme shaking of an earthquake is a rare phenomenon, and the current design philosophy says that we could have damage in them should that extreme condition appear on the structure, subject to the fact that the structure doesn't collapse under that level of shaking. So the linear analysis that we have learned in the undergraduate program will have to be augmented by a nonlinear analysis at the master's program. And once you have a background of how to do nonlinear analysis, then you'll be able to understand the exact behavior of the structure when it is subjected to ground movement or base loading or base displacement, as would happen in an earthquake condition. So one of the most important points to remember is that under earthquake shaking for normal structures, damage is expected. The only challenge then would be, where would you admit the damage? Would you admit it in the soil, in the foundation, in the columns, in the beams, or in the slabs, or in the walls? This is the question that comes under the realm of the Indian standard, where we would like to guide the designers to ensure that the damage is controlled and it is only in specified locations and not everywhere in the structure. Another important point that has to be remembered is that at any location, there will be three types of ground shaking. One is called the minor shaking, which is supposed to happen very regularly. It's a small level of shaking. A moderate shaking, which occurs occasionally, and that would really take the structure into damage condition to some extent. And then a severe shaking, which would be a rare event, but it will really put large amount of structural damage in the structure. Now, the earthquake resistant design philosophy itself says that under minor shaking, which is frequent, no structural damage should occur, no non-structural damage should occur. Under moderate shaking, some amount of non-structural damage is expected, and maybe a little bit of structural damage initiation is also likely. On the other hand, during severe shaking, structural damage is admitted, but no collapse has to be ensured by the designer. Let's see if we are really doing this in our standards right now. If not, what is it that we can do in time ahead? So designers know that there are four things that have to be considered in the design of structures. And these four things are called four virtues because they are the good things that you must have in your structure. The first is that it must have a good configuration. The structure must be simple in plan and in elevation. It must have a regular grid in the X direction and Y direction in plan. And it must not have any undue large masses tucked away at any elevation, undue large stiffnesses incorporated at any position in the structure. The second most important point was stiffness. That means during the small levels of shaking, the structure should not swing too much because then the damage will be much higher in the non-structural elements like the windows and the false ceilings and so on. The third point is the strength. The structure cannot have a large amount of strength if you want to make it economical. So we limit the strength, and that is also specified by the standard. And the last requirement of earthquake resistant structures is good ductility. Ductility is basically the capacity to deform inelastically and not collapse at the end of that shaking in inelastic domain. So the Indian standard will focus on these four aspects, and you'll see how did this evolve over time. First, let's look at the history of development of standards. The first question was stiffness. So the level 1 design scheme that we have internationally, was stiffness based. This is where it was considered that if I have a large structure, stiff structure, then we will be able to resist earthquakes. But while stiff structures reduce the deformation, it was also that the stiff structures are made with some material, and so it would have large mass also. So the mass became a liability, even though stiffness was an asset. And it is this mass that is actually causing havoc in the behavior of structures. So if you look at time, a large number of historic heritage structures were traditionally made with stone, mud, and they were made massive. And it was noted that in 1556, in an earthquake in China, 8.3 lakhs of people died, and the area destroyed was 840 square kilometers, and about 60% of the population was killed in some of those districts that are there in that region. So that was the level 1 design, meaning this was the pre-standards situation. Intuitive design it was, and it was thought of stiff structures will be able to resist earthquakes, but history has shown to us that dynasties have collapsed because of this kind of large stiffness structures, which also brought in large mass, that they were not able to resist earthquakes. And time and again in India also we noted that when earthquakes happen and we have these massive structures, they are not doing too well in the country. In the recent Nepal earthquake also, we saw some large heritage structures coming down because again the large mass issue that is there. So this is when the formal development of Indian standards has started after level 1. That means we're talking about level 2 onwards is when Indian standards started. And that was with a focus on force. So Indian standard had stiffness in mind, but in addition, it introduced the concept of earthquake design force. You notice that we have significant collapses of buildings with intermediate stories or the lower stories coming down, or even water tanks coming down, parking sheds coming down. In all of them, most of the stakeholders thought that earthquake applies a force on the structure and the structure should possess large lateral strength. But they could not provide large lateral strength because we did not want to pay more to make the structure stocky. And so we could design only for a lower level of force. As a consequence, we jeopardized the safety of the structures. So earthquake design force is in focus. How much should be the design force? Very clearly, earthquake design force is acceleration times the mass of the structure. And the question was, how do we estimate this acceleration? Design horizontal acceleration value. And this was noticed that initially this seismic force was taken to be a constant value irrespective of the size and shape and geometry of the building. And so it was taken to be about 10% of the weight of the building. That was in the 1920s. In the 1960s, it was learned that taller structures actually are flexible and they do not draw so much force. That is because the earthquake shaking itself does not have so much energy in the range of those natural periods of structures which are very long. So in 1984, we saw that in Indian standard, we introduced the concept of soil flexibility. So we had hard rock, soft soil, medium soil, and so on. So we introduced the understanding of flexibility of the soil underneath the building, the layers of the soil underneath the building. And so that was level 2A design. I'm breaking level 2 into level 2A and 2B. Level 2A was that we use a certain force for design along with the stiffness, but it was learned that there was no relationship between how much stronger should the vertical members be compared to the horizontal members and so on. So this is called strength hierarchy. That was not a significant aspect. Also, the design of the vertical members, the PM interaction diagram was adopted, but the shear was not calculated based on the formation of plastic hinges in the members, and it was independent of the PM interaction that was used in those members, both for horizontal members and vertical members. So what is the status of the current codes that we have in India? So once again, we took this matter of ground movement. We thought that we should recognize that the movement of the base will impose a certain displacement, relative deformation in the structure. And so for that, can we then see if we can ensure that the structure has got large deformation capacity in the horizontal direction? We wanted to incorporate ductility for reversal. So the codes now had certain amount of steel on both faces requirements and so on. And the issue of no collapse came back into focus. So the method of calculation of the force was that, first of all, consider that the structure is linear. It doesn't have any damage, and that's the green structure. And so you will get a certain force, and that is called the elastic force, elastic maximum force. And then we'll bring it down to the design level. So 3 levels of shaking that we know of were incorporated in this. The first aspect that got introduced in a significant way in the standard was the concept of seismic structural configuration. You take any structure and you can classify them into convex forms and concave forms. Convex and concave are very interesting shapes, where in convex, you take any 2 points which are sitting in the body of the geometry and join them with a straight line. That entire straight line is inside that geometry, inside that 3D object. Any 2 points on that, if you join it with a straight line, it'll stay inside. But if you come to the concave shapes, if you take any 2 points, there will be some cases where the line will not stay inside the object, but will come outside the object. And what it means is that when inertia force is generated at the roof, let us say, that has to be transmitted to the ground. This path, this line joining this, will be the direct path. But in the case of concave structures, we will not have a direct path, but we'll have a load path that is bent. And you know that when 2 force lines are not collinear, then there will be an unbalanced force, and that unbalanced force requires special design. And it's not always possible to do special design continuously along curved surfaces and so on, and hence we accrue a lot of damage in concave shapes. So this time around, the Indian standard brought in a significant list of items that are acceptable, that need to be incorporated to make sure that this kind of a damage is not induced by the choice of the geometry of the structure. So very clearly, convex forms or convex shapes or convex geometries of structures is what we will be looking for in earthquake resistant design, and not concave forms. You can see that classically, if you have a rectangular building, that will do well. But if you have a L-shaped building, that will do very poorly during an earthquake. If you want to look at more shapes and plan, the rectangle and the polygons with the convex geometry are better than the alphabet shaped structures. This concept is valid both in plan and in elevation. So one must look at vertical irregularities and horizontal irregularities as part of the requirement. And that is what the Indian standard is saying, that we need to have vertically regular and horizontally irregular structures. One of the noted earthquake engineers said, if you have a poor configuration to start with, all that the engineer can do is to provide a band-aid, meaning it can improve basically poor solution as best as he can. Conversely, if we start off with a good configuration and reasonable framing system, even a poor engineer cannot harm its ultimate performance too much. Just to tell you in examples of numbers, if you start with a poor configuration, you are 20% efficient. And the best engineer worldwide, if you bring, he will make it 23%. On the other hand, if you have a good configuration, you're already starting with 85. And the poorest of engineers can keep it only at 85. He cannot bring it down further. But a very good engineer can take it to 98%. And so the use of an engineer is more effective only if you have a good configuration to begin with. And so the important point here is that architects and engineers have to work together. Architects should provide forms that are supposed to be convex in nature and supposed to give good earthquake behavior. And then an engineer can put in her or his best and make that structure outstanding structure. So the current level of the Indian standards is that we have good seismic configuration requirements, a reasonable initial lateral stiffness specified, and also a minimum lateral strength is specified in these structures. Now, you notice that when we go into construction, we have prescribed requirements for ductile detailing. And when we use such ductile detailing, sometimes when member sizes are too small, this detailing becomes very cumbersome and concreting is not very successful. I must also mention here that the focus on connections has to be understood very, very clearly. While it is true that the entire design is being, attention is drawn only to members, that is beams, columns, slabs, footings, and so on, the critical point is still the connections between beams and columns, columns and foundations, and so on. The traditional understanding in, let's say, steel structures, you will see Professor Satish Kumar dwell on this over the couple of days in this particular webinar, that steel structures have a large spectrum of connections admitted in design standards. And these connections are weak, flexible, semi-rigid, and rigid. As you would see, more is the relative deformation in the connections, more will be the damage in the connections. And it is not always possible that the connections can be repaired after an earthquake. In case of steel structures, it is possible that we can even attempt it. But in the case of concrete structures, where concrete beam column junctions are severely cracked, it is unlikely that we can restore them back to their original glory. So the traditional design procedure for new structures requires that all connections are rigid and not any of the others. But if a structure already exists, it may get classified into these, and that is the responsibility of the designer or of the engineer who's assessing the strength of these existing structures. So the concept of ductility has drawn attention now. We are interested in what is the maximum deformation that is likely to be sustained by the structure with respect to the yield deformation, and that ratio we are calling it as ductility. So larger is the ductility, better is the structure for earthquake shaking. But what is interesting to note is, even though steel has a ductility as a material of about 300, and concrete has a ductility of about 3.5 at a material level, the net ductility in overall structure does not exceed about 2.5, 3.5. It doesn't exceed that. What it comes out to be is the weak link will determine the ductility of the whole structure. And in reinforced concrete, the weak link is concrete and not reinforcement. Sometimes reinforcement can become a weak link if you do not have enough confinement of transverse reinforcement holding the longitudinal reinforcement. But in general, if you do good detailing, even with the best detailing and the best construction, best sizing, reinforced concrete will have a limitation, because concrete in nature is actually a brittle material and does not have large ductility. But in the case of steel structures, you think that you will get large ductility, but even there, the connections will play into force and will limit the ductility. Even if individual members are stocky, they don't have buckling at the local level or global level, the member connections will come into force, and that will reduce the ductility significantly. So in 2002, the concept of ductility was brought in with the response reduction factor put in the denominator of the calculation of the design base shear. This response reduction factor, 2R, is the one that is obtained from various experimental and analytical studies that are done on structures. So you would consider the structure to be linearly elastic. That is the elastic maximum force that you're getting, and then you will reduce it by the factor of R, which is ductility reduction factor and overstrength reduction factor, and this will be your design force. So the design force is only a small fraction of the elastic maximum force. This is typically about 10 times lower than the maximum force. If you have a good ductile structure, if you have a brittle structure, this can be 2, 3, 4, 5, depending on how well we detail our structure. But even if you design it for a certain level, let's say HD, the partial safety factors for loads and materials and the redundancy in the structure will give you a higher strength in the structure when actual displacement loading is applied, and that strength is the H max on the structure. So the maximum strength induced or of the structure, which is characteristic to the structure, will be higher than the design force that we are using in earthquake calculation, earthquake force calculation. So this is the important point to remember, that the calculation procedure assumes that you have an elastic structure, then you reduce it with the reduction factor, you obtain your design force and go forward. Another important point that has now in 2016 come into force is that the attention has been drawn to a desirable collapse mechanism. But it is still not incorporated, but one step was taken in that direction, and that is crucial. Let's understand what is a collapse mechanism. When you take a structure and you apply lateral forces and push them horizontally, damage will be induced. The question is, where should the damage be? Should it be in the vertical members or in the horizontal members? Very clearly, vertical members are supporting the horizontal members, so vertical members should not have much damage. Only horizontal members should have damage, and that is the first principle, that the column has to be stronger than the beam. Now, where in the beam can you have damage? If you look at bending moment diagram under lateral sway, you will notice that the bending moments are largest at the ends, and so that is where we are expecting damages to accrue. But of course, in case you have a concentrated load, sharp concentrated load sitting somewhere in the beam, then you will see that the beam will have another plastic hinge in the middle also. But in general, we are talking about uniform loading, and in that case of uniform loading, we are saying that this will be the typical desirable collapse mechanism, where all the beam ends have plastic hinges and the bottoms of the columns. If only the beams form plastic hinges, then the structure reduces to 4 cantilevers here, this particular structure. That is the left column, the left interior, right interior, and right exterior column will become 4 cantilevers. It's still not in the collapse state, and for collapse to occur, you will require this rotation to hinges to form at the basis of the column also. So this mechanism is to be predetermined and pre-decided by the engineer before starting to design. That will lead us to deciding who is stronger than whom. If beam is weaker than the column and column is stronger than the beam, then we need to know how much stronger. And the Indian standard now tells you that the column has to be stronger than the beam by a certain factor, and that is the beginning of incorporating a desirable collapse mechanism. By ensuring that the column is stronger than the beam at each node in the structure, we cannot guarantee an overall collapse mechanism. And that's our next worry, that while the Indian standard is incorporated seismic structural configuration, minimum lateral stiffness, initial lateral stiffness, reasonable initial lateral stiffness, and at least a minimum lateral strength, the intent of the standard is that we must provide good ductility, and that is currently through prescriptive detailing. And the intent is that we must have a desirable collapse mechanism, and that is again coming through only in part is coming through the column to beam strength ratio that has been incorporated in the standard. So that gives you the 2B, design level 2B, that we are adopting in the country, where there's a strong column and a weak beam. And the design of members for shear is now dependent on the PM interaction of individual members, both for beams as well as for columns. So when you look at the force design, the item 2 here and item 2 here, completely taken care of. But item 1, strength hierarchy, is only partially taken care of in the case of the capacity design method that we have. And this is an important departure from where we started from force design. A little more on collapse mechanism. The collapse mechanism is not getting guaranteed still, because we're only talking about column to beam strength ratio and not making sure that the hinges are formed throughout the structure. Currently, the hinges are getting concentrated in the lower part of the structure and not moving to the higher part of the structure. Many reasons for this. One of them is that the loading is less severe here, and the lateral sway actions are dominating the lower story because of the flexure and shear deformation shapes that the structures are going into. Now, as each hinge forms here, you would form on the backbone curve, on the load deformation curve, a little departure, and the structure gets soft by that much. So this top portion, these people are not participating in national development. And so they are actually becoming a liability. So only when each individual contributes, then the nation will grow, and that we know very well. Likewise, in structural design also, only when all members contribute plastic actions, that is when the structure will be able to swing much more towards the right. For example, we are saying here about 750 mm in this structure. You can take it further down only if everybody else participates. Second point, even if everybody participates, the first hinge that is formed here and here, the first hinge has to continue to rotate till the last hinge is formed. And that is another big demand, which is plastic rotation accruing in the members. Now, if all of these hinges happen slowly, one after the other, then the first hinge has to rotate by large amount. But another option is that these hinges can happen almost together, so that you will be able to see that all of them together can, like you see here, there's no hinges here, and all of them are starting together, and then they should be able to go further down. Now this part here will get activated if you change the column to beam strength ratios a little bit, and then you'll be able to see damage in those also. Maybe the column sizes are oversized, the reinforcement is much more than required, both in beams and columns, and so we have to investigate as to why this is still remaining elastic in the structure. So from this, what we're learning is that everybody has to participate, and the collapse mechanism, the desirable collapse mechanism has to happen, and the first hinge has to continue to rotate till the last hinge happens. So those are the two demands. So the global collapse mechanism has to be predetermined. It is not left to the structure to decide what it wants to do. If you have open ground stories, parking lot structures, they will collapse immediately. In half an hour, they'll just come down. If you have tall stilted structures, they will also be weakly done. If you have weak columns in the upper stories, they will cause trouble to you. If you have an inner story where you put glass everywhere and made a restaurant out of this floor, or a gym room in this floor, then you are in trouble. All these are practical situations that are arising in buildings that are being built across the country today, and hence our focus has to still go back to creating a good mechanism. This is not to say that you should not have a restaurant in the intermediate story, but this is to say that after you recognize that the intermediate story has got a restaurant with glass all over, then how would you design it? Your structural analysis should recognize that and still make sure that the columns in this do not form hinges, in this story do not form hinges. So while prescriptive detailing is giving you some amount of solace that yes, I have taken care of ductility, the fact is all the prescriptive detailing need not necessarily give you the best ductility, and that depends on which member are you looking at and where is the member located, how much is the load on the member, what is the support condition or the end condition of the member. So ductility is still not quantified in the Indian standard. We are looking at an intent through prescriptive detailing, but we need to quantify the ductility achieved in the structure. So for the structure that we had, let's say we have a structure of 2R equal to 10 and overstrength is 2, then ductility factor is 5. So the question is, does the structure have a ductility of 5? So if we start here 0.05, am I getting 0.25? The ratio, normalized displacement ratio. It's not clear. And that needs to be verified. And that is why we are looking at a closed loop method for design in the standards to come. Right now, we have a material, we know its stress-strain relation. We go to the section, we get the strength out of that, and then we do the detailing and forget about it. We don't know whether indeed how it is behaving because we have not examined each member for the different cross-section, different materials that we're using, and different amounts of steel that we are providing. So while we know that material is completely understood, section is understood, we are still having a gray line that prescriptive detailing is good enough or not. And finally, we don't know our load deformation behavior of structures in normal design strategies. And as a consequence, we don't know the hinges that will be formed, whether they're acceptable or not. Thus, we notice that in the forward loop only, we're putting in some effort only in step 1, 2, and maybe 2.5 here. But to the remaining part here, where the ductility is coming in members and it is coming in structure, is not understood yet. And of course, we don't know whether these hinges are going to be formed as per the desirable collapse mechanism or not. So the earthquake resistant design.
Can take a break and have what?
Pardon?
So you can take a break and have water, sir?
No, we don't need a break. Don't worry.
Okay.
So if you want to design a new structure, you have the Indian standard, you apply the clauses and design the structure. And then if you want to know its behavior before the earthquake happens, you apply the synthetic records, or you apply a ground shaking analytically in the computer and see whether the structure is going to behave as you desire or not. And then when the real earthquake comes, you will see that you will be able to understand truly whether this behavior is acceptable to you or not. Right? That's the design of new structures, where you start with the design and then do some analysis and understand what that is going to give you. If you're happy, then you say, I've done my bit and the design is complete. And if this analysis gives you desirable collapse mechanism. But the true test is not here analytically, but the true test is the real earthquake. When that comes in, what will be the behavior of the structure? There are always surprises. So many earthquake reconnaissance studies we did, we saw that even in the so-called ideal structure, we still had some embarrassments. Now, if you have an existing structure, you start with the ground motion applied on that structure and you understand its behavior. You would say that, no, this is not acceptable for me. I need to do retrofit. So I go to the standard, I change the structural system, I add elements, I modify some structural components, and then I do the design for the retrofit. And then I wait. And when the earthquake happens, I see that the structure has been analyzed by the earthquake. And that is what will tell us whether truly what we provided as retrofit is sufficient or not. So there's a small difference between design and assessment. Design is you start fresh with materials, you have all the freedom. In assessment, you don't have any freedom because the structure is already there, material is already deteriorated, and the sizing is already fixed and so on. So assessment should be done by very experienced engineers, not less than 20 to 25 years of experience. While the design can be done by those competent engineers who are looking at about 5 to 10 years experience. This doesn't mean that as soon as you graduate, you'll not be able to do analysis, design, or retrofit, or the analysis for new structure. No, you can do. Only thing is the authority to approve this is not yours in the early days. It is of the senior engineers who are competent, who have seen a lot more than you have, and do have the eye to catch errors very quickly. They also know that the uncertainties that arise in the mass, in the stiffness, in the damping, and in the ground motions, what is the implications of that? And hence we are looking for competent engineers and not just qualified engineers. If you get a degree, you're qualified, but if you have understanding of the behavior of structures, only then you will get to become competent. And that is what we are looking for, that only through experience of hands-on projects and activities that you'll be able to achieve this competence, and not by mere qualification. Also, in time ahead, we expect that there will be examinations for competence checking. Every couple of years, you will have to write an examination, and that examination will tell you whether you are abreast with the latest in the subject or not. So continuing education will be necessary. That means you have to keep attending seminars and short courses at reputed institutes so that you'll be able to get the latest knowledge through those programs. And then you will have to read a lot of books and also read a lot of international documents and do enough work or investigation at your end in your offices so that you will be able to say, yes, there is a need to change and this is the direction of change. So that's the current status of the Indian standards. And let's go to the future in time ahead. So we talked about level 1 design, which was stiffness based, level 2, which is strength based, and we are now coming to level 3, which is deformation based. So where are we? This was level 1, only stiffness part, and then level 2 included 2A included the first 3, 2B included the 4, and then maybe a part of 5. And now what we are saying in 3, you require deformability. Now what is deformability? Let's understand that. Now I have a structure, I've designed it for certain initial stiffness, certain strength, and so I get this backbone curve by doing pushover analysis of the structure. And this is the characteristic of the structure. Characteristic means it's like your name. If anybody asks you who you are, you tell your name. By telling your name, you're actually reflecting the entire pedigree of yours in academic terms, in personal terms. Now, this is the maximum deformation that the structure can be subjected to. Clearly, if the earthquake is saying that the maximum shaking is this much, then your structure is safe. No problem. Because remember, I started and I also emphasized again that earthquake is displacement loading, not force loading. Watch this. If the earthquake was force loading, after this force, the earthquake will cause collapse of the structure. That is not happening. Earthquake is displacement loading. Even if it crosses the peak value, even if it comes here, it still has an answer. If it comes here, it has an answer. If it comes here, it has an answer. So what we are seeing here is when the earthquake imposes a maximum deformation, which is less than the capacity, deformation capacity of the structure is safe. On the other hand, if the earthquake imposes a maximum deformation, which is beyond the capacity, equilibrium will not be satisfied. Internal resistance is less than the external demand, and hence the structure will collapse. Therefore, the third generation of design standards, that is what we are working towards, is to actually develop a procedure which is called displacement-based design procedure. So displacement means relative displacement between bottom and top. How much should that relative displacement be? So what is the capacity and what is the earthquake asking? So from in the earthquake demand side, you are familiar with pseudo-spectral acceleration, which is the basis for the design lateral force in our standards. So its own relative is spectral displacement. If you take PSA and divide it by omega square, you get SD, spectral displacement. And for that natural period of the structure, you can choose that, you can pick the maximum deformation that's coming, that's at the centroid, and then you scale it up to the roof if this load deformation curve is using roof as the basis. And so this will become your benchmark. If the earthquake demand is here, this structure is insufficient, you have to do something so that this point, the capacity point, comes to the right of the red demand line. That will be the game of displacement-based design. Just to get you a little idea, so I have 4 structures designed, and the green dots are your capacities, deformation capacities. So I have an earthquake which is being resisted by all the buildings happily, no problem. Only thing is the small building, the chota, the less lateral force design, low lateral design force structure is going to give me more damage. The intermediate design force structure gives me lesser damage, and this one has elastic behavior, and this one also has elastic behavior. Now, if the earthquake is a little larger, the first building has collapsed. No questions asked. The second one is breathing hard. Third one is finding difficulty. The fourth one is still having a easy breeze. Now the earthquake has gone further up. Second building also has collapsed. Third building is on the brink, and the fourth building is having difficulty. And now it's intensity 10. All designed reinforced concrete structures will collapse. That is what MSK intensity 10 is saying, and that will be the condition of this one. So if you are not estimating your hazard correctly, you will have collapse. If you estimate your hazard correctly, you should not have collapse, if provided you design for deformability in the structure. And this will become the basis for our third generation design standards that we will prepare in this country. As you notice, not so much focus is on the vertical axis. The whole game is only on the horizontal axis. Just to quickly compare, we have initial stiffness as a basis and design force as a basis so far, the current standard. But in time ahead, initial stiffness always will be there because under small shaking, we should not have too much of flexibility, but the focus will go away to delta capacity and not to VB. VB is the design force. No, we don't worry about that so much. We want to worry about delta capacity. But of course, in the early days when we are going from this method to this method, we will still have a minimum lateral force specification that will anyway be achieved for this kind of deformability, but it will be there in the clause, but the key focus will shift to delta capacity. So that's your deformation based design, where stiffness, strength, and deformability all are coming into picture. And on the horizon is one more issue that we have to address, and that is energy. So what is energy? Once the damage begins in the structure, inelastic energy is getting expended in the structure, and that inelastic energy is what we are interested in, and we would like to quantify the total energy that the earthquake is giving and the energy that the structure can absorb. It is the competition between these two. If earthquake is feeding a certain amount of energy and the structure is able to absorb that energy, no problem. If the structure is not able to absorb that energy, yes, there is difficulty. So how do you understand energy? Energy has lateral deformation, this one, lateral force, this one, and initial stiffness. So all these three together are related to energy. So in this diagram, out of the four quantities, three will be related to each other. So let's understand. So in time ahead, all of us need to believe that earthquake induces a force in the structure and does not apply a force. It induces, right? And so the structure should possess all the things that we have discussed so far, up to 6, and now a 7th one, which is guaranteed energy absorption capacity. So you can imagine we are at about 4.5 here, and we need to climb this. So it's a steep climb, it's a mountain climb here. But if all of us work hard and all of us are sharp in our subject and are able to understand quickly, we'll be able to achieve this target reasonably early. Now, let's understand energy a little more carefully. Energy, ground motions have three characteristics. One is amplitude. How big is the wave here? How big is the ground movement? Duration, how long does it shake? And frequency content. So you can see this one, very low frequency. You can see this high frequency, and then a mixture of the two, and so on. So amplitude, duration, and frequency, all three are important for us. So different earthquakes worldwide have shown that we just can't put them in one box. We need to quantify the earthquake energies for a particular case. In a particular region, you will get a certain type of shaking. In a different region, you will get different types of shaking. So more or less, energy has to be quantified for each region independently. Now, let's say this is the total energy that the earthquake is feeding into the structure. And out of that energy, viscous damping, which is structural damping, which is inherent in all structures, that is taking away this part, the bottom part. And this is the top part where kinetic energy or strain energy is there. Here, the structure has no damage, it is elastic. Now, earthquake has stopped at this point, but you still see that there's large kinetic energy, which means unless viscous energy rises and finally absorbs away all this kinetic energy, the structure will not halt. This might take about 2-3 hours after the earthquake. Now, that's a very discomforting situation, that earthquake is gone and that it will take forever for the structure to come down to quiet now. So instead of that, let's say we allow some damage. If you allow damage, this viscous damping energy is already there, and then this green energy is what you're absorbing away in damage. And as you can see here, the kinetic energy has reduced even as the earthquake is coming here. So this is a good situation to be in, that you're able to absorb that energy and not make the building swing further after the earthquake is over. The catch is, how would you create this energy dissipation? hysteretic energy dissipation. There are two ways. One is through structural members. Beams will form plastic hinges, and so you'll absorb energy at all beam ends. The second one is that you keep devices, specific devices for absorbing energy in the beams, in the interface between beam and the column, and so on. There are different strategies depending on whether it's a steel structure or a concrete structure, or a brace structure or a wall structure. There are different strategies for putting devices, and then you'll be able to dissipate energy in them. Therefore, the critical point is to make the building get quiet after the earthquake by dissipating large amount of energy through nonlinear actions in specified locations or specified components, which are not necessarily main structural components, but part of the load path of the structure. So that component which is absorbing energy, should that have this kind of behavior where stiffness is getting dropped down, also strength is getting dropped as you load the structure into larger displacement, or should you have a nice big loops as you swing back and forth? Understandably, the right hand side is your choice, not the left hand side. Now, sometimes some studies have shown that joints also can dissipate large amounts of energy, especially in steel structures. Now, that's not a good situation to be in, because once joints get into this kind of inelastic action, the building tilts, and that will cause trouble in terms of having a permanent drift in the building after the earthquake is over. And this is crucial for us to make sure that the joints do not undergo damage during strong earthquake shaking. So once again, if the current strategy is stiffness and strength that we are looking at for design, in time ahead, it will have stiffness, it will have delta max, and it will have some energy. And obviously, if three items are fixed by the standard, the fourth can be calculated. It will be interrelated. And therefore, design force will become a consequence of the choice of energy, deformation, and stiffness. So that's energy-based design. And if I put all of them in big picture, let's see, stiffness-based design, we left it. This is prehistoric times. Strength-based design has two parts, force design and capacity design. And force design is also outdated now. Capacity design is in practice right now. Deformation-based design is under development, and energy-based design is on the horizon. So where do we use each of these methods? The force-based design was intended for normal buildings in low seismic regions, capacity design for high seismic regions, and for special structures, even in low seismic regions, you need to put capacity design. And this deformation design should be critical on lifeline buildings and structures, mandatory for that. And even for normal buildings in moderate to high seismic regions, they should become mandatory. So in time ahead, if you are looking at developing earthquake resistant structures in the country, your knowledge also has to now step forward in terms of understanding deformation based design and energy based design, right? So earlier we said 4 virtues, and now 4 has become 7. 7 virtues of earthquake resistant structures: configuration, stiffness, strength, ductility, which were the old 4, and now it'll be deformability, desirable collapse mechanism, and energy absorption. These will be our 7 watchwords, 7 virtues of earthquake resistant structures that are supposed to be built in time ahead. Now, so far, until now, whatever I talked about was about capacity of the structure, resistance of the structure. Now I need to emphasize a little more about demand. As I said, delta capacity is fine. You are able to do some analysis, get delta capacity. You can do experiments and get delta capacity. But delta demand, how do you get that? Now that's the very tough question. And that is where colleagues like Professor Raghukant are working on this for some decades now. And they want to come up with a better understanding of nature. Of course, nature is always above us, and we are only trying to work hard to understand some part of it. So we will be falling short in our demand estimation, but we will continue to work and keep improving our own understanding. So severity of an earthquake was deterministically obtained based on past earthquakes. But now probabilistic methods are coming where we will look forward and say, if there is an earthquake on that particular fault and the earthquake is of a certain size, what will be the shaking? So futuristic projections are happening, and that is where we need to understand a little more about surprises that have happened to us in the country in the past. 1967 Koina earthquake, the peak ground acceleration was 0.63 G and the intensity of shaking was 8. So if you look at the current zoning, the peak ground acceleration, the zone is taking us 0.24 G. So we are off by a factor of 3 in trying to estimate reasonably the current seismic hazard in the peninsular India particularly. And if I look at the 93 Killari earthquake, the peak ground acceleration was 0.5 and the current seismic zoning says 0.16. Again, a factor of 3 or so we are off by. So peninsular India will have bigger surprises than the Himalayan India, because in Himalayan India, the hazard has gone, the estimated hazard has gone closer to the actual hazard, but I'll show you that in a minute, that even that is under question now. For example, India, the peak ground acceleration, the 4 seismic zone goes from 0.1 G to 0.36 G. And let's see. So in the peninsular India, we know that this is still higher values can be expected in time ahead. So in design, we're even taking half of it. That's even worse. So if you come to probabilistic methods, you need to choose a probability. You must say, no, I don't allow even the likelihood, least likelihood. So you have to choose a likelihood and then you can choose an acceleration. So if you say, no, I allow 2%, then I get this. If you say, no, I will go below 2%, 0.5%, then I can get higher acceleration and so on. So if you say the severe structures like nuclear power plants, you say, I don't allow any choice. I will take what is coming exactly. In dams, you say, I'll take some chance. In lifeline structures, bridges, pipelines, and so on, water lines, and so on, you will take some chance. So you'll reduce that peak ground acceleration to a smaller value. And in bridges, you'll reduce it to a further value, and buildings, you'll reduce it to a further value. That is in the design calculation. The acceleration used is getting reduced because we are admitting damage. So what we're calling this in the case of all structures other than nuclear power plants is called maximum considered earthquake. And in the case of nuclear power plants, we'll say maximum credible. Whatever is likely to happen, we will use that as it is. But in this case, what is likely to happen, we will not use that, but we'll use a value smaller than that because we are taking chance. We are taking chance. We are allowing probability to hit us. The reason why we are doing that is, as you come to the left, the number of structures increases by orders of magnitude. So the cost of investment in structures is increasing. That is the reason why we are always worried about what is the peak, what is the maximum design force. For example, there's a map of the acceleration, peak acceleration values considered in this region, right? New Zealand says 1.2 G, Japan says 1 G. They're sitting on the interplate tectonics. We are also sitting on the interplate between Eurasian plate and India, but we are saying no, we are at 0.36 G. So let's look at it. Our response reduction factor, the denominator here we're dividing by, is about the smallest alongside Mexico. But if you look at the design force that we are using, acceleration design coefficient, ours is the lowest value. Of course, brother Nepal will change its numbers quickly, so it can go away from it. But right now they are looking at the similar number. Pakistan is about twice as, Iran is about 50% more, Turkey, Iran. Greece is about 3 times. Japan is about 3 times more force. New Zealand is about 3 times, 2.5 to 3 times more force. What we're saying is, as you design for higher forces, you will get lesser damage during earthquakes. And that is what is shown in normal building systems itself. The design coefficient is much higher in countries that have put priority on safety more than what we have done in this country, right? So I pray that we will go close to what the actual hazard is, and we'll be able to design structures for higher coefficient so that we'll be able to save our lives much more than what we are able to do now. Because we are under designing structures, while the world is looking at a MSK scale, if you have a MSK scale value and the corresponding PGA value, the world average is sitting somewhere here. But in our case, in India, our average is lower. That means our structures are able to resist for the same PGA, are able to seeing much higher level of damage than the internationally well-designed structures. So that is a worry for us, that if you are looking at a design for the same peak ground acceleration, our structures are seeing much higher damage. For example, Ahmedabad is sitting 225 kilometers away from the earthquake. We saw an intensity of about 7, but then the structures have collapsed, and that is not acceptable. In the 2001 earthquake, that is not acceptable. You cannot have under intensity 7 collapse of reinforced concrete structures, because the MSK scale itself says that at 7 you will have damage, but you cannot have collapse of structures. That's a worry that we need to worry about. So we talk so much about cost. We need to be careful that should you pay more money initially, you will have less damage. If you pay less money initially, you will have more damage. This curve is very clear. At the same time, if you spend more money initially, you will have less retrofit costs later. And so obviously there will be a situation where we will have a minimum. That means for the same cost, we have two structures. One is to the left and one is to the right. So if you see this as the minimum, to the left of the minimum, all green, and to the right of minimum, all red. This red is because this is where we are talking about damage, destruction, loss of life, to the right of this line. And to the left of this line is where we will have no damage, no loss of life. The question is, where do we put this line? Should it be at this minimum? Should it be little to the right, little to the left? Where should it be? Studies have to happen now to do cost implications of structures, so that we'll be able to set the initial cost and the life cycle cost both into focus alongside retrofit cost. So we need to have more of our colleagues to spend time on understanding cost implications of design that the Indian standards will propose. So if you took a return period of 500 years, you will get certain peak ground acceleration values. But if you take a larger return period, you will get 10,000 years. So if you take 10,000 years, the hazard level projected is 0.7 G to 1.5 G under rocky conditions. And if you take the 500 years, you will get 0.5 G to 1.2 G. So this is where the issue is, that we want to make sure that we incorporate realistic acceleration values. Currently, we are using 0.36 G for Himalaya. So we may have to raise that a little bit in time ahead. As I mentioned, that displacement is also a focus for us. And in general, we will have both horizontal displacement as well as vertical displacement. And if you do studies of the various past earthquakes, you will see that the displacement is up to about 700, 800 millimeters, which is 0.7, 0.8 meters. That's a pretty large amount of displacement that we are noticing. And also the velocities will be much higher in the near field. You can see that as you go farther away from the earthquake, you will see lesser shaking. Look at Ahmedabad, which is sitting and it's supposed to have only 1.6 centimeters of shaking, but then buildings have collapsed. Why did that happen? We need to investigate that carefully and make sure that this situation doesn't arise again. This is from the 2001 earthquake, whatever happened in the Bhuj region, Anjar, Kandla, and then if you come farther away, Ahmedabad is seeing very little displacement, but then major collapses. Those are the issues that will worry us. If you look at here, 8.5 centimeters, vertical is about 10 centimeters. This has caused significant havoc to us in the east-west and the vertical components. So Professor Raukant is doing detailed finite element analysis of the Earth in the Indian region, and then telling us that, look, up to about 200 kilometers, you will have the effect of the earthquake displacement. That is bound to happen. And then, so if you are looking at this Himalayas where the big earthquakes will happen, you are going to see about 200 kilometers. That means this entire Indo-Gangetic plain will get shaken by this severe earthquakes that we are seeing. And that is the reason why we need to look at earthquake hazard once more in this country a little more carefully. And that is what Professor Raukant is doing along with his students in this subject. So faults are there everywhere in the country, but how big an earthquake can happen in this interior fault versus in the Himalayan thrust faults is what the entire guessing game is. And so experience will tell us how much should we consider in this seismic hazard analysis. If we don't do it correctly, then nature will take over. The earthquake will tell you the correct answer, but that will be an expensive answer for us. So we have to be very careful to take such expensive answers in time ahead. Now, if you look at this pipeline design, you might think, who's the crazy designer who's doing this all bends and turns? Well, it's not a crazy designer. He doesn't know where the fault is, and he says it can go to the left or to the right. So I will not make a straight pipeline, but I will make a slightly curved pipeline so that if the shaking goes back and forth, the pipelines are resting on horizontal rails and free to slide back and forth. So this is called compliant design. There are two ways of designing. One is you hold the pipeline and then see what are the stresses induced and design for that. Second is that you don't hold the pipeline, allow the pipeline to swing back and forth. If it is 800 millimeters, you will be able to see nice movement back and forth, 0.8 meters, and that will suffice for design here. But if you're going to get 2 meters, 3 meters movement, then that's a worry that will require this pipeline to actually have enough flexibility in it so that it can straighten up during that large levels of shaking that will happen. So deformation demand is needed. We need to know what is the demand coming out of this earthquake so that we can design our structure to be safe. So in 2016, we started this harmonization process. Ductility-based design in 2018 got introduced in our activities. And now we are looking at a deformation-based design. Let's see another couple of years if we can do that, and then finally energy-based design. So this is the roadmap that we have from 2016. I hope that in the standards that we have right now, we have two important standards, 1893 and 13920, that are on focus in this particular week also. This is the demand side and this is the capacity side for concrete structures. We are preparing a similar one for steel structures. Professor Goswami, Rupen Goswami, who's going to speak tomorrow, is going to talk, actually leading that effort on steel structures. And we have a number of other standards that need to be developed. But every time there's a demand standard and there's a capacity standard that we have for all types of structures. And there's also an assessment standard that you're seeing, seismic evaluation and strengthening of reinforced concrete structures. So I'll stop here by saying that we're in a process of revising our seismic zone map. We're also looking at if we can estimate displacements and come up with design of buildings displacement. Base isolation standard should be released soon in public domain, and the seismic design of buried pipeline also is under advanced discussion. Seismic design on non-structural elements should also come in soon. So this year, if we are able to come out of this lockdown, we can do some work and move forward. So I'll stop here by saying that our development of standards has been slow in India because there are only 11 players in the arena here and everybody is on the galleries watching. So if India has to go forward in terms of developing the standards quickly and revising them regularly, more of the people should leave their benches in the galleries and come into the playing field and become partners in the development of the standards. Of course, everybody doesn't have to do big things. In fact, none of us has to do big things. Each of us has to do a small thing. If you can move that out of your way, that will be fine. But if you say it's not my job, then it's a tough situation to be in this country. But whether we do work or not, nature will do its work. It will tell us whether our calculations are right or wrong. And so we should not be embarrassed by nature in time ahead. As part of the bigger question of disaster mitigation, we are looking at policy, practice, safety, education, typology. A large number of activities have to be done in this country. And you will notice that they can be grouped under 3 sets of activities, which is knowledge, skill, and attitude. Work has to be done on all of them, and from left to right, and implemented from right to left. Once you go forward, if you understand in the forward direction, then you can start implementing in the backward direction also. But one of the important elements in this entire process is actually developing standards, right? So what are these 3 blocks? Knowledge, skill, and attitude. That's competence, actually. Competence is a nonlinear combination of attitude, skill, and knowledge. And if even if you haven't guessed, let me tell you that the most important of all of these is attitude. And I would then say that what we require is that teachers would have to come out of this understanding that earthquake is a force, and knowledge analysis has to become part of the curriculum, and seismic design codes have to be revised regularly. Otherwise, there will be too much of a new learning every time the code gets revised. The nation has to have a uniform development of education, practice, as well as in development of standards. This is very clear that we need to protect every citizen and that we have a large amount of work to do. But if we can inspire ourselves, and we'll be able to go a long way. I'll simply say that from untruth to truth, from darkness to light, and from life to eternity, we should be able to make progress consciously in this country and make this country a much more safer place in time ahead. I'll thank by saying my regards to Professor Binu Sukumar for inviting me to speak to you all today this morning. And I hope that you will become partners in this process of development of standards. Jai Hind.
Thank you so much, sir. And the participants can post their questions in the questionnaire, the question answer box. And the participants also viewing in the YouTube platform, you can also type their questions over there. Our moderator will pass those questions to this Zoom platform, and resource persons can answer all those questions. So please post their questions in the question answer chat box. Already there are a few questions, sir.
Yeah, there are a few questions. I'll take these as they are. There's a question by Professor Shanmugam who says, what about beam column joints in earthquake resistant design? Sir, this is already there in IS13920, and it is a section on design of beam column joints. You will have to design for the demands that arise out of forces that accrue from stress resultants coming from structural analysis, especially involving earthquake loading in it. And so we will improve that section, but it's already there in our Indian standard. Dilip Kumar is saying there is no past experience of earthquakes in our region, but in the last 6 months, we experienced nearly 50 to 60 shakings in the region of Telangana border to Andhra Pradesh in Deccan Plateau. Yes, actually, our memory is very less, but shaking has been happening for almost millions of years. And the more we know about the subject, the more we are conscious about it. And hence, you will notice that the ground shaking, particularly in the plateau region, the south of, let us say, the Indo-Gangetic plain, I showed you that satellite picture, the rocky part of it, that is going to give us surprises. In fact, there are already spots that seismologists are keeping an eye on. And Telangana is not a surprise. It's if you look at the mountain ranges, you will notice that wherever there are mountains, there will be shaking, because these mountains were created out of compression of in the plateau region, the tectonics, south of, let us say. So I would say, no surprise, we are going to expect more shaking in time ahead. Is going to give us surprise incorporated in the seismologists has it seismologists, and Telangana is not a surprise. And Telangana is not a surprise. If you look at the, you will notice that wherever there are mountains, wherever there are mountains, there will be shake. Madam?
Voice disturbance. There is some voice disturbance.
Yes. So what I'll do is, should I go out and come in, or looks like right now it's gone? So let's.
It's okay, sir. Now you can proceed now.
Will buried pipelines and tunnels be considered together for earthquake protection? Yes. Buried pipelines is already the standard is getting developed. So this year it's in advanced stages of development. This year we should see, hopefully by the end of the year, that standard also coming out. Tunnels, we have not written any standard yet, but there is interest in developing standards for tunnels. So I hope that we will be able to come up with something for tunnels. What is the R value for base isolated structures? So let the structure, when the standard come out, I should not take away the thunder of the people, but I can assure you that it's going to be different below the base isolation and different above the base isolation. You will see that in wide circulation. It is supposed to come up soon in wide circulation. Then it says in the hysteretic curve, you have said good and bad. Can you please elaborate more on that? Yes, please join a master's program in earthquake engineering in one of the reputed institutes. You'll learn all about good and bad of ductility, but you should read some international books. It will not be fair for me to spend more time on it. Basically, all I'm saying is the area inside the hysteresis loop per loop has to be large. Only then it's good. If the area is small for one loop, then it is bad. If you do brittle detailing, if you don't have enough development length, if you don't have enough confinement, you will get small areas and small loops. If you have good confinement, large column sizes, large beam sizes, you will get a very good hysteresis loop. So I pray that the condition will improve with ductile detailing. More importantly for me, the column sizes, beam sizes we are choosing, column sizes particularly, beam is okay. Column size we are choosing is very miserly and is actually the biggest, I would say, the factor that is affecting safety of structures. We seem to worry about carpet area in square inches. 1 inch square is a worry for us in carpet area. I don't think we should lose our perspective of safety. We should still say that we respect life more than money, and hence I will allow column sizes to be a little bigger. That's the only game that I think architects can do a lot more interior decoration and improve that. Okay, looks like Dilip Kumar is asking a lot of questions. Is it same for both?
No, sir. Dilip Kumar is he's posting questions in the YouTube, sir.
Oh, questions.
Yeah, Dilip Kumar is a moderator. Yeah,
I understand. So now I understand that from YouTube. That's why he's writing YouTube also. Why damping ratio is same for concrete steel as per new code? It will remain same because it is design procedure. The damping value is different. The structural damping is, that means the initial inherent damping is different for different structures, which is 0.5%, 2%, 1%, 3%, 4%. These are the different structures that we have. Same concrete structure as a building and as a chimney, it is different. So what we're saying is that when severe shaking happens, this damping shoots to 20%, 25%. So the initial value becomes very small compared to the large value that is there when damage-based hysteretic damping is occurring. For that reason, since all the initial damping values are not the true damping that are happening in the structure, internationally, 5% damping is used as a basis for design purposes. Actual damping will be much higher. So it is not that there is a correct value for damping. In fact, nobody knows how to model damping also. Damping has to be understood as an unknown, and we have to be very modest. Whenever we talk about damping, we have to talk with respect because we don't know anything about it. We don't know how to do mathematical modeling also. We are under illusion that we think viscous damping is the correct one. There are many other damping. Those people will swear that those are better, whoever is proposing whichever method. So right now in engineering practice, in earthquake engineering practice, the biggest humility factor is damping. We don't know much about it. So we'll use some value. Internationally, we all agreed that we'll do 5% as the basis for design. Rest, whatever happens, is what has to be seen. If the behavior is not good, we don't change damping value, but we change the force values up and down. That is what is the game. Is it same to consider both RCC and offshore steel structures? A question is not clear, but I'm saying the design philosophy, the principle of earthquake resistance is the same for all structures. The only question is, if you are not allowing damage, you are making it elastic, you are making your structure expensive. Otherwise, it is the same. How do you consider stress strain curve in earthquake resistant design? In the design of new structures, we don't consider stress strain curves of the softening part. No, we don't consider. If you have seen IS456, it will say steel elastoplastic. The curved part is going and we'll get a steel elastoplastic, let's say like mild steel. And in concrete, only it rises to a peak and then stops and becomes a plateau. There is no dropping part in concrete. There is no rising part in steel for the design purpose. However, if you have a structure that exists and you want to do assessment, you have to take the true stress strain curve of the material and use that in assessment. But for design, we say, I hope all the manufacturers are doing correctly. I hope that this is the behavior of concrete and steel. I hope that if that is the behavior of concrete and steel, that the calculation I'm doing is a reasonable estimate for the strength of the member, right? Okay, so are there any efforts about codes exclusively for multi-hazard? We are trying to learn one hazard at a time. I hope that after, I pray that more groups are there about each hazard and trying to improve for each hazard. And then in practice, when you do design for a structure, all the loads come on together. The person who is integrating all this is the design engineer. So obviously you need experience, 20, 25 years to say that if wind is applied and earthquake is applied, which one governs and all that. You don't decide a priori which one governs. You do the calculations and show which one is governing for each structure every time. There is no statement to be made beforehand. And there's no fear about multi-hazard. You have to do good things related to the earthquake design. You have to do good things related to the wind design, wave design, blast design, temperature design, all the good things you have to do. Okay. Dynamic analysis must for all building seismic irrespective of height. We are doing STP. Don't talk about projects, sir. Let us not talk about projects. Ask pointed question. In analysis of building, can we consider beam column joint as rigid? If you have made the beam column joint strong enough, then you can take it to rigid. If you have not made the beam column joint strong enough, you cannot take it.
Certificate correction. Second foot correction.
Can we improve structural or hysteretic damping? Structural damping, you can't do much. It is there inherent. But hysteretic damping, yes, you choose energy dissipating devices, you place in correct locations and you'll be able to get that. Can we use dampers for dissipating energy in complex structures? Yes, in complex structures, there's no correct answer. Make simple structures and use dampers. It will become successful. If you use complex structures, you don't know. Complex into complex is very, very complex. So don't make complex structures, make simple structures. Why in India base isolation method is not much adopted? Well, it will be, now there's a standard, it will get adopted. Seismic resistance can be provided by steel fiber reinforced composites as stated in literature instead of seismic ductile reinforcement as stated in Indian codes. Well, if somebody can show us literature, we can consider this, but right now nobody is providing us details on steel fiber reinforced composites as a basis for the structural members. Nobody has given us that detail. If you give it, then we'll be able to take it. Can seismic resistance be provided by, no, that's gone. Which code should we follow for base isolated building currently in India? Base isolated. Currently, until the new standard is there, there is no standard. So your client has to decide which standard to use. But once this standard comes out this year, then maybe you should use this standard, or not maybe, that you will be using this standard. Okay, it looks like I missed some questions. Let me go back and check. Buried pipelines, R value for base isolated, can we expect in a book in India? By December, possibly latest. If Corona were not there, I would have told you timelines. Because of Corona, I don't know the timelines. So I'll say, I'll be positive by December we should get it. The code on base isolation. Differentiated, okay. RC structures, softening, pipelines, higher values of response reduction factor. The world has adopted much higher values. Overplayed, if you see, our 2R values are international R values. So there is some confusion in that. We'll get rid of this 2R if we can, then we will become at par with the international R values. So there is some confusion right now. So let's hope that we can examine that in detail. What will be the changes in seismic codes when 456 is revised? When 456 is revised, seismic codes will change to the extent of how to calculate moment capacity, but the principles of seismic design should remain the same. Principles should remain the same. The factors, the limiting moment factor, limiting moment calculations are coming out different now. So we will have to examine those factors a little more and see. So in general, the code will not look very different. The numbers might change here and there. Detailing will be about the same. Column to beam strength ratio will change a little bit. Okay, I'm going to the, can any advancement be made in terms of prefabricated structures as earthquake resistant components? One of the key things in prefabrication is connection. And so the major requirement for prefabricated structures to get accepted as earthquake resistant structures will be full-scale testing. And since we have only limited number of full-scale test facilities in the country, our progress is slow. But as we build more full-scale test facilities in the country, we should be able to make prefabricated earthquake resistant structures also. But extensive experiments have to happen. There's no doubt about it, because full scale is the way out. In small sized small members, the concrete and steel bars, even to reduce the diameter of the bar, the concrete is having higher bond than what is there in the real structure. So bond properties, the tension properties in concrete, the swings, the displacements, amounts of swings of displacements, all these have to be done full scale, and therefore it is best to do them on prototype rather than on scale models. So full scale testing will take us to prefabricated structures, answers to prefabricated structures used in seismic areas. Which earthquake code is the best in the world? Well, what is good for one country is not good for another country, because nature is not the same in both countries. So there are standards which are using advanced knowledge of earthquake behavior. There are standards which are using not so advanced standards. Countries which have earthquakes on a daily basis are more conscious of it, and they are making changes more consciously and quickly. And countries which have occasional earthquake are doing it slowly. So if I look at it, then Japan, New Zealand, Australia, and Japan, New Zealand, and America are the ones that have more robust standards. Canada on the top, Mexico on the bottom, Chile in further south of America, South America is actually, they are having, so large number of countries have very good standards. There's not one, but large number of countries, each of them focusing on one particular aspect, strongly. And so I would say there's enough good literature around, enough good examples around. You have to use them for our good. But we cannot copy those standards into our case directly, because on the analysis side, we can look at a clause and say, yes, this analysis procedure is fine, because analysis is universal. When it comes to design, the design codes are different. Partial safety factors for loads and materials are different. Load combination for different loads is different. And so, and the method of designing the components is different. A limit state method we use, somebody uses LRFT. So we have to be very careful when we borrow design clauses, but we can borrow the clauses related to analysis rather more quickly because it's behavior related. It's mathematics rather. Which code is best? We have already done it. And which code should we follow for base isolated building currently in India? That we've answered. Currently, you will follow what your client says because there is no standard. But as the Indian standard comes out, you'll use that one. Generally, as per the code, we take earthquake or wind load in combination and not both. On what basis earthquake and wind assumed do not occur together? Well, internationally, it is agreed that God is not very unkind, that he will give you the worst earthquake and the worst wind on the same day. That is the reason we are having immense respect for God, and we say that we will go with only one natural hazard at a time. That's the standard agreed principle. So we are following the same here also. For pre-engineered structure, what special measures shall be taken for earthquake? First thing and the only thing, full-scale testing. Anything that you say on calculation is not sufficient. For cast in situ, there are a huge number of experiments done worldwide. So you can take data from there and learn from there and get confidence from there that yes, this is fine. But if you have a pre-engineered structure, everybody is pre-engineering in one's own mind. And it's on paper. What we want, do a full, if you're doing a 3-story structure, make a 3-story structure, test it and shake it full scale. That is the only way you can build confidence. Or if you're having a multi-story, more than 3-story, you take a typical story and test that typical story with 1 story below and 1 story above as holding facilities, and the middle story will be in focus. So full-scale testing is essential now, especially because in pre-engineered, the game is to economize and speed up the construction. Whenever economy is taking the driving seat, I think the answer should be through explicit experimentation to show that these structures indeed can resist large lateral deformations, relative deformation between bottom and top in each story. Okay. Gravity load resisting system for lateral deformations. Very interesting. Structures, all structures carry both loads, vertical and lateral. And if you have in a structure, let us say a 5-story building, if you have RC walls, and RC walls are taking 95% of the lateral force because RC walls are very stiff and they are not moving too much, then the interior columns, which are together taking 5%, and if there are 20 columns, 5 by 20, 0.4% each, then you say that no, it's not carrying too much of lateral force, it's only carrying gravity. So I will call it a gravity load resisting system, right? And this is in your hand as a designer. You provide an element, you can be braced frame, it can be a RC wall in a moment frame, or it can be a full RC wall in certain bays. in certain grids. In all those cases, gravity will load will become smaller and smaller on the interior columns as you make these special earthquake resistant frames or grids to become stiffer and stronger. In that case, there's a clause in IS1893 which says deformation compatibility has to be guaranteed. You check what is the actual displacement that these so-called gravity columns will swing by. Additional P delta moments will be there. Those have to be considered in the design of these members. And so there's no opinion about this. There's a fact right now. You follow Indian standards IS1893 part 1, and you will notice that every time you have a structure in which you have very stiff members designed to resist the full earthquake force or maximum earthquake force, the remaining earthquake force becomes very small component. And so these other columns will become gravity columns. So I pray that you look at the Indian standard. What is the full scale test mentioned in PEB? I can't repeat more. I can simply say, take your full structure, push it horizontally, and show us that it can take large deformations without collapse. You can't, if you think it is a too long a building, take the slices of those buildings, let us say 3 bays by 3 bays or 3 bays by 4 bays, test it, push it in the weak direction, push it in the other direction, as per full loads that are likely to occur. When I say loads, I'm saying deformations, I'm saying displacement loads. I'm saying how much is the relative displacement that the top and bottom can resist. Please do that test. I heard from most clip, I don't know what it is, a most clip, structure can become earthquake resistant, but it can't become earthquake proof. Is this right? Yeah. So if you buy a watch and you turn the watch on the backside, it is written 50 meters water resistant. That means that you can wear that watch and go into a swimming pool or even in a river, and up to 50 meters, the company is saying water will not enter that watch. But after 50 meters, company is saying that no, I have no guarantee. If you go below 50 meters, if you do deep diving in an ocean to do some scientific work, we will not guarantee that this watch will work at that level after you come back. Which means that is earthquake resistant, that is water resistant. 50 meters water resistant. It's not waterproof. Any depth you go, if water doesn't go inside, that is called waterproof. Likewise, in an earthquake, because we don't know what is nature and what is the maximum hazard that is likely to come, and we're only estimating. So the standards worldwide will simply say, for the estimated hazard, if you do design by this method, you're likely to have no collapse. That is what the earthquake resistance is all about. But if there are surprises, it will cross the line and it will be a difficult situation there. That is why we are very modest in our language, and we use earthquake resistant rather than earthquake proof. Earthquake proof means we are behaving like gods. We know everything. If you do this, nothing will happen to your building. No such guarantee in any structure. For the hazard level known, only for that resistance is guaranteed. In a weak story and soft story, which one is compulsory check of earthquake resistant design? Both. There is no negotiation. Both are important. Left eye and right eye you are asking. One is stiffness and one is strength. All this hour and 10 minutes that I spoke, the focus was always all of them. You need to have initial stiffness. You need to have minimum lateral force, strength, design forces to be guaranteed, minimum lateral design force. So you need to have both taken care of compulsorily, weak story and soft story. Both are bad. Both have to be corrected so that there is no weak story and there is no soft story. Soft story means suddenly the stiffness has become very less in that story. Weak story means suddenly the strength has become very less in that story. You put large columns but plain concrete, no steel. So once it is cracked, suddenly it fails. No strength at all. Which foundation is best for RCC for more earthquake resistant structures? Don't ask specific questions. I mean, questions like medicine for everything. No, that kind of game in professional world doesn't help. What we should say is that how do we design structures for foundation? I mean, how do we design foundations of structures? Normally, the starting point of foundation, the choice of foundation will be non-seismic consideration. After you have chosen that, you have to evaluate whether that foundation is going to be suitable or how its design can be modified to resist earthquakes in an efficient way. So the choice of foundation is still, to start with, will remain the non-seismic condition. And once that is chosen, we evaluate the acceptability of that foundation. For example, you say you've done pile foundation. Then I come and then say, okay, liquefaction is occurring. First 6 meters, there's liquefaction. So I consider resistance only from the remaining part of it. And then we have 6 meters of liquefied soil. And there is a small gentle slope of 3 degrees or 5 degrees. And that liquefied soil is flowing around the piles. So there'll be extra drag force on it. So now you consider drag force on those piles. Or I have a bridge across Ganga River, railway bridge, and I have a well foundation. Scouring is a normal scour level is, let us say, minus 20 meters, and then extreme scour is minus 40. So I've anchored it to 70 meters. So I have 30 meters of anchor. So now I will do earthquake analysis for the 30 meters of the well foundation anchored into the into the soil. So it is not that you start with this with earthquakes as a basis for choosing the foundation. No, you start with the basis of non-seismic loads, and then go and then do check whether the suitability is there for seismic design. Which foundation is best? Looks like all the questions are taken care of. Any other?
You answered, yes, sir. So you have answered almost all the questions, sir.
Yes.
I think this is a time to wind up. And,
it's time to wind up. We're also 12 o'clock, so obviously.
Yes, sir.
The promised time of 2 hours, we are there.
Yes, sir. And the feedback forms and the assessment, it is given the link, and even the link will be even sent to your mail IDs, and it will be active by 2 p.m. Every day. At the end of the session, you have to give the feedback as well as the assessment, and it has to be completed only if you complete all the 5 assessments at the end of all the 5 sessions, then you'll be eligible for getting the certification for this program. So thank you so much, sir.
Thank you once again, madam, to you and to
Principal.
Thank you, sir. Thank you.
Yeah, Professor Junaid, thank you once again.
Thank you, sir. Thank you, sir. Excellent, sir. Excellent presentation. Very good interaction. Thank you very much, sir.
Yeah, grateful. Grateful for the opportunity.
Thank you.
We'll keep in touch, and maybe someday we'll
definitely, sir. Definitely, sir.
Thank you.
We are honored by your presence, sir. In this.
Grateful. Thank you.
Thank you, sir. Thank you. Yeah. Thank you, all other dignitaries. Dr. KP Jaya, madam. Thank you, madam. Dr. Raghukant, sir. And Rupan Goswami, sir. Thank you, sir. Thank you, madam. HOD, madam. Thanks for organizing.
Thank you, sir.
Very nice event. Thank you.
Thank you, madam.
Thank you, sir.
Madam, if you could copy all the questions and keep it in a Word file every day.
Okay. Sure, sir. Okay, sir.
Thank you.
Ma'am, shall we wind up, ma'am? Jay ma'am is online, I think, ma'am.